I'm Michael Taylor, and I'm here to talk about some RISC-V related activities that we're doing at UC San Diego, in particular in my research group, the Bespoke Silicon Group. So if you think about the typical Bay Area software startup, and in particular its software stack, it looks a lot like an iceberg. So down below the surface of the water is this huge amount of open source. It's basically, the collective crowdsource efforts of the world over the last 40 years. And then on top of that is this narrow sliver of software, which I call the innovation layer, which is the company's value add. Okay? And so in this kind of system, you have this enormous leverage where you have this very small amount of code you're writing on the top, and then you're just leveraging this huge ecosystem below it. And it's this kind of leverage that allows Instagram, for instance, to take $500,000 and 13 people and then build a $1 billion startup. So one of the things that would be interesting to consider is, what does that look like for hardware? Okay. So if software is an iceberg, then hardware is an icy mountain. Okay. And like with software, we still have that innovation layer, which is at the very top of the mountain. But unfortunately, right now, everything below it is just a pile of rock. A lot of closed source IP and tools, elbow grease kind of hardware design that we need to do, like packaging and PC board design. So I think it'd be very interesting that, we should be considering, how do we build that fully open source ASIC stack? So I have a dream, which is I can install a fresh copy of Linux on my system, and then the only thing I have to do is pull some stuff down from Git, some tools and some Verilog or BlueSpec or whatever it is. Maybe not BlueSpec because it's not fully open source. Oh, that was a burn, I guess. Then type make, and then boom, out comes GDS, right? Everything is open source. I can look at it. If there's a bug, I can fix it. If I don't like it, I can improve it, right? So in my group, we've been working on maybe filling in some more aspects of the stack. Of course, we're all here for RISC-V. And we're all collectively trying to address the top of the stack. But there's other parts of the stack that I think are also very valuable for us to address, so we can get that kind of leverage that we see in the software startup world. So starting with RISC-V, if we go down the stack, of course, if we're going to build a chip, you need I/O pads and standard cells. Now, fortunately, if you're doing 65 nanometer or older, you can often get this for free from the fab. But even though it's free, I would still rather have open source, because then I can share it with people. Right now, I have NDAs. Anytime I want to share anything, I have to go and figure out how to extract all the stuff that's not public and then maybe ship it to somebody. So it makes it very difficult to have that kind of shared ecosystem. Below that, if I want to have more than 200 megahertz clock in my chip, I'm going to have to go get a PLL. And then if I want to actually talk outside the chip quickly, then I'm going to have to go buy some IOs, whether it's 100K for LVDS or $1 million for a DDR4 core. Right? Then there's the tools. Now in academia, we get them all for free. That's great. Not so great for startups. But even though I get them for free, I would still rather have open source versions, because then I can go fix bugs in them. I can figure out why it's doing what it's doing. And then once again, I can share it with other academics. All over the world, we have all these universities independently building their own CAD flows. Because of this sharing problem, it just creates a lot of replication and a big lack of leverage. And then at the very end, even once you have your part, you need to create a high performance package for it. And even if we open source our existing packages, we would actually like to have something a little different, which is something that's reusable and repurposable, which is not a typical feature of a package. And then, of course, below that is the PCB design that chip is going to sit in. And it's the same kind of parameters that apply there. We'd like it to be reusable as well as open. So here's a random thought. Wouldn't it be neat to have a standardization of some kind for sockets for RISC-V hardware, and maybe a standardized motherboard for it? And heck, why not? If I'm going to ask for all these things, why not a chipset that's a single chip that has all these expensive IP cores that everybody can leverage when they're building their RISC-V based hardware as a separate chip that you can just buy off the shelf? Okay. So in our little project, we are attempting to address some of the different aspects of the stack, in particular the ones that aren't free to universities. So I'm going to tell you a little bit about that. So we have this project called Base Jump, where we basically have defined a socket interface, and in there, of course, goes your RISC-V IP, and then your innovation layer, whatever that is. And then we also have a library of standard hardware components. So the idea is to raise the level of abstraction for hardware design. The idea is that, if we have all these standard components, I'll show you what they look like later, then, we can stop reinventing the wheel constantly and start building bigger and bigger things that are open source. So after you tape out your chip with these components, we have an open source package, which supports the socket interface. And then we have an open source motherboard, whose main job is just to try to get your ASIC talking to some kind of FPGA board that has those expensive IP cores that I would like to replace with some kind of chipset. So this is a slide that shows some of the components that we have in the BSG IP cores library. So it's standard kind of things that you think about in hardware design, like priority encoders and counters and crossbars and graded binary, high level things like FIFOs and round robin arbitrators and stream mergers and stuff like that. But also some of those key elements I mentioned, like an open source clock generator to replace that PLL that you might have to buy for $50K, and a high-speed I/O interface that would replace at least part of a high-speed IP core that you might buy for that purpose. And so we've actually had a bunch of early adopters of this infrastructure. So on the right there, you can see a board that was designed by Princeton, where they actually modified our motherboard design for their chip, which was fabbed in 32 nanometer. And then that board has since been shared with multiple universities, including UIUC and MIT. Now, of course, at this point, you're like, where's my RISC-V eye candy? Like, he's talking about all this non-RISC-V stuff, so I'll throw this up here. This is a recent chip design we did that's going on a TSMC shuttle run in a couple of weeks. It has 10 RISC-V cores on a single chip. And our plan is to basically release end-to-end all of the files for this chip, including the Verilog source files, all the RISC-V implementations, but also the package design, the PCB design, the firmware, so everything. So the idea is to kind of have a snapshot of the full stack, minus the CAD tools and the standard cells, which we're getting for free. Now, what's on this chip? So we have a standard tile that we're replicating. There are 10 of them. It has a router and then also a processor, and it's using a remote store programming model for multi-core. The pipeline is something we designed ourselves. It's a very lightweight core. It's a 5-stage pipeline, not a 3-stage pipeline, so it's a little faster than your V-scale implementation. And it's a very small core. It's about 50% SRAM. And in implementing it, we're leveraging this open source library we have with the system Verilog building blocks. We also have the clock generator to generate the clock, and then also the high-speed I/O interface. So when we implemented this, we actually found there's really good density. So the large chip there is a previous chip that I worked on with the team at MIT, the MIT raw processor. Implemented basically in the same process generation, I can fit 10 cores in the same area as 1 core in the MIT raw. But in order to do that, we threw out things like floating points. So it's not entirely apples to apples, but certainly you can get very good density, and the RISC-V implementations are very small. We have another design that we're currently working on, which is a 16 nanometer TSMC SoC. It's going to use a large array of those small cores. It's going to have 2 rocket cores with the L2 complex, and then a neural net accelerator, and then kind of all the infrastructure I mentioned for doing I/O to the outside world. Okay, so in our group, we've made a couple of contributions to the RISC-V ecosystem. They're what I call docu contributions. They're basically documentation, especially centering around the ROCC interface, trying to help folks in the community come up to speed on using ROCC with the Rocket core. So we have something we call the ROC doc, which kind of collects all the information about ROCC in one place. And then also we have a tutorial on building accelerators with the Rocket interface. So there's been a little traffic on the forum or on the email list. You can check it out. And Anuj Rao, who's the key author of both documents, is here at the conference if you'd like to talk to him. So I'm going to end with 2 slides. This is the first one. First is maybe a set of recommendations. Now, as was said earlier, it's hard to know everything that's going on in the community. So this is just our own viewpoint from our perspective. But one is that we think the ROCC interface is fantastic, but we think it'd be really nice to actually wire that up to the top level of the rocket hierarchy. And that way, your accelerators are kind of first level entities on the chip, and it's much more easy to wire I/O devices and things like that directly to the core without having to tunnel them down through the layers. And then the other recommendation is that I think it would be very useful for the RISC-V community to have, at least yearly end-to-end releases of everything, putting a stake in the ground saying all of these versions of this thing work together. And then when people are trying to modify things and innovate on their own, then we have a concrete version that everybody is looking at and can discuss. So right now, the kind of, oh, well, just download top and refer to top model means that everybody's effectively working with slightly different versions of things based on when they pulled it. Okay, so I'm going to conclude here. The work we've been doing in the group essentially is looking at trying to build that full open source ASIC stack. And we've been kind of working at many levels trying to fill in the gaps to get you that kind of end-to-end open source hardware stack. Okay, thank you.
Hi, Arun Thomas, BA Systems. So I really liked your presentation. I thought it was great. I mean, having a fully open source ASIC would be awesome, full stack. I was wondering, I liked the recommendations you had at the end. I was wondering if there were other pain points you had with RISC-V that your group had in general, other things that the community could be doing.
I think the biggest one is to have, if we have silicon implementations, to ideally have all of the files and versions collected together for those silicon implementations, put them on the website, and have the like if there's like if you're hacking the Verilog file to do the final steps, put that Verilog file on the web too, so that people can get as close to replicating what you did as possible. I think that will reduce the amount of effort for everybody.
She's the one in the middle there.
Frank Schameister, Cadence. So the actual deliverable of what you open source as part of your project, can you talk more about how you choose the formats? I mean, if I look at the EDA portion of it, Verilog vendor A, B, C are not always the same Verilog and so forth. So how do you do the actual locking in of the formats, and how do you choose the formats?
I see. So for in terms of the HDL, yeah, we use System Verilog, and we're pretty good about picking a subset that is synthesizable across many vendors. We do FPGA emulation, so we have with running on VCS and running through Design Compiler and running through Vivado. We've checked it with 3 different implementations, at least of the parser. For more of the like package/PCB stuff, we're not using any particular open source standard. It's basically pads. Yeah. And yeah, we have Gerber files. We actually have gone even a step further. We actually put receipts for all of the vendors for all the chips that we buy, so you know exactly what the bill of materials is, and also like even the files that you send to the PCB manufacturer to specify all the thicknesses of the layers. So really getting into the nitty-gritty. Should you actually want to go and modify that file and then go send it somewhere? We're trying to provide all of that information, not just here's the file, good luck, but even almost to the level of email chains with the vendor, so that all these questions, like what is the finish that you want on the on the package to do wire bonding, those kind of questions would be very difficult if you haven't done it before to answer. So we're going to try to provide that too.
Alkim Roa from Omchiways. So can you comment? I mean, this question is related to the last one. So can you comment a little bit more about the highest PIO and how you're going to deliver that? I mean, highest PIO is so dependent of layout. and schematics. So I mean, can this guy just ask, are you gonna break the NDAs?
Right. So I'll talk about that. So for the high-speed I/O block, our goal is basically to get higher frequency than somebody would get, any individual group would do on their own, to get higher quality, so that at least people look at what we did and then save time, and would be tempted to use it over doing it themselves. With that said, yeah, we're not trying to push the limits or write any papers on how fast our I/O is or anything. Our goal is basically just to get the highest performance out of LVC MOS that you can, because those are the standard I/O pads that are provided by the fab. So the I/O channel is basically a high-speed source synchronous I/O channel. But part of our goal is to put baselines in place, and then people who are even better at designing whatever it is than us can look at it and say, boy, that's really crappy. I'm going to do a better version. And then hopefully we'll see a rapid upgrade across the stack of all the things that we did. With that said, we actually have done very good designs of these things, and I would say they're quite good implementations for what they are.
Got another one up here in the front, Michael?
Hi, Rishi Nikhil from BlueSpec. So the open sourcing presumably allows people to make variations on this. So what is the sort of verification story on that? Presumably, it's going to be a lot of work in just getting this verified itself. So are you planning to release systems by which it's going to be easy to modify and re-verify?
So in terms of verification, I mean, basically our goal is to release the verification suites that we used for all of these components. But beyond the native support of System Verilog for verification, we don't intend to make any innovations there. But certainly, it's verification is a very costly part of hardware design and often overlooked. So I agree. I think it's very important.
Got time for one more, I think. Anybody? Oh. Two more.
So just how fast is it?
How fast is what?
The processor and the high-speed I/O and.
Oh, okay, yeah. So the 10-core multi-core chip is in 180 nanometer, and it's 400 megahertz, which is about as good as you would imagine getting in 180. And then the I/O, it's basically just pushing the limits of whatever your LVC MOS can do.
Okay, thanks.
Okay, we'll squeeze one more in.
Don Stark from Google. So one of the things we're seeing at advanced process nodes is the fabs are actually limiting your ability, even if you design something, to sort of release the GDS, because they're saying it basically shows what the design rules are. Do you have any thoughts about how we might deal with that as an open source community?
Yeah, that's a great question. I've also thought about that a little bit, because we would like to, I mean, all of our stuff is standard cell design, so that's one way to do it, is to say, we're releasing scripts that arrange standard cells, and we don't tell you what's inside the cell. And that's our approach with all of this stuff. But I guess the alternative would be to write scripts that pull in the design rules and generate what you need. Or even, I mean, even crazier thing might be like, I don't know if the GDS vendors would sign off on this, but to have basically encrypt your stuff and use as a key the intellectual property that is being guarded. So you use the design rules, some hash of the design rules as your key or something like that. So to kind of lock those together and make sure one person owns the other. I know Moses, for instance, has had situations where they will guard a set of IP that is closely linked to, say, TSMC, and then in conjunction with your NDAs, with TSMC, you also get access to this other stuff that is sort of closely linked to it. I don't think that's necessarily an ideal model, but it's been done before.
Great. Thanks, Michael.
Thank you.